Okay, we can start today. Thank you, of course, to be here. We can start today with the variation of the Kalman filter. I hope that I will be able to tell you about two possible variations. One just at the end, fleshing out. Uh, but the first one is extremely interesting, which we will start directly now, including also the simulations. And in the second example, related nevertheless to this similar structure. The structure I intend. Kalman filter represented or with the model represented in output. Do you remember when I introduced the Kalman filter, the EKF, the extended Kalman filter? I told you what I'm doing now. That we have also the possibility, excuse me, the possibility to represent the model, or we have a part of the model in the output. Um, of course, this is interesting because how possible to say, second, let me share. If you remember, we have, in this case, in the EKF in particular, and Jacobian, H capitalized, which represents the approximation, the Taylor approximation, or something similar, mm, with the nonlinearity if we have a nonlinear part in the output, which must be considered. 1 second and I come back to you. Yeah. And this is basically the topic of today, because the idea is to give you the possibility to be flexible in thinking uh, about possible variation of Kalman filter. We have seen cascaded, extremely important. We did many considerations related to the observability, even though I didn't tell you many things about that. But the basic aspects to be known um, are basically considered. Do you remember I tried to express the difference between local weak observability and weak observability, and that we have in a test, excuse me, just for the local weak observability. But if you separate, I didn't insist on this, but if you separate, of course, we have a delay in the observation, but this delayed is not something which is then just a drawback, because delayed means also large movement, and this means it could be that the system, even though we need more time, but becomes not only local uh, weak observable, but observable uh, or weak observable. But let me say observable. This means if I separate, it could be that we have the drawback that we need more time, uh, but nevertheless mm, yeah, we can nevertheless work, no, with this kind, let me say, with this kind of separation. Anyway, I don't remember what I told you, but for the examination in the context of this course is not so, let me say, extremely important to go in depth on this, but you have at least an idea, and yeah, and very important for us in a little bit more the implementation according with the time which I have um, at disposition. Okay, 1 second. Let me look at the material, and then we will start. Okay, this is the the material of today. Let me look a little bit here. Mm, I think I have it. Mhm. Okay. Yes. Let me see what I shared until now. Okay, I think you see the presentation. This means I don't need to open this. Let me go to the topic of today. Yeah, the topic of today is this one. Look, let's consider these two equations here, or these two dynamics. We have a nonlinear system because we have x2 squared. Now we have two states, x1 and x2. The dynamics is clearly here represented. X2 squared says to us that the system consisting of two dynamics is nonlinear. The parameter A is an unknown parameter that must be estimated, or that should be estimated. So we repeat a little bit the concept of the estimation of a parameter, and thanks, because of the presence of the of this parameter A to be estimated, we have another nonlinearity now here, because if I augment A as in a state, this means derivative of A, which we called here x3 dot equals 0, we have another nonlinearity here. Of course, this nonlinearity is an augmented nonlinearity, if you want. Is sometimes we call artificial, but in the sense that we introduced this nonlinearity uh, in order to be estimated. To be more precise, is also in the estimation of the rest of the element which we want to estimate, x1 and x2, because we assume that A change over time. No? Do you remember, I didn't put here A of t, but anyway, is implicit, no? As I told you until now. At this moment, not is new. Look at this. I repeat it for you, the system which we want to represent in the Kalman filter. As I told you many times, the test of the observability must be done for the representation which we have, because it's the representation which is observable or not, because we want, or we need to work with the representation. In our hand, we have just a representation. The physical system or the systems in general unknown. I mean, through the model isn't the representation, we can try to estimate, we can try to control the physical system or the systems, if you see. From this expression here to this here, the difference is just I am using here forward discretization. About the forward discretization, I told you many times. I don't have time to go in depth on this, as I told you many times. But the forward discretization, Euler forward discretization, should be a little bit added. The specification, Euler forward discretization, or the forward Euler, better to say. We obtain this expression here. TS is a simple time. Everything already, let me say, at least introduced in different context. Context means examples. Look at this, x3 of k equals 3 of k minus 1. Always this. This is a common expression of the Gaussian variable, because we don't know anything about the parameter a. Of course, As I told you, I didn't present any example, but of course, if I know something about the parameter A, some physical insights can be considered with its derivative here. What I intended is, if I intended as A change over time as a constant, multiply an exponential function up to minus 3t, of course, I have to consider, and then I have to put not the derivative equal 0, but the derivative exactly what I have for the derivative. And in this case, I try to estimate, for instance, the amplitude of this exponential function, which I have to consider as a Gaussian variable. In any case, you say, I have a Gaussian variable. Yes, but the phenomenon is described more in depth because we know that this Gaussian variable A is multiplied by an exponential function. Anyway, I didn't do the example, but in some projects it could happen that we can go more in depth together in the project. If I don't know anything about the parameter x3, or let me look here A, of course, this hypothesis here is the more general hypothesis, but of course, it's something which basically cost because the variable x3 is a Gaussian variable inside the Kalman filter without any knowledge or pre-knowledge. If I include some structure, of course, the Kalman filter can work more precisely. We pay this price, do you remember? If we are not so precise in the sense in the representation, in the covariance matrix, or better to say, in the approximation or the estimation of the a posteriori variable in terms of variance. If we don't have knowledge, if the system is less observable, of course, we get the mean value, but with a large variance, oscillations around this value, which we want to estimate. But we get as long as the system is observable. Of course, we are not sure that we get because extended Kalman filter is inside and how possible to say, yeah, not convex optimization problem. This means the optimality is not guaranteed, but also the convergence. We have to start relative close or in the convex region of a point I hope that is the global minimum which minimize the variance. Let me see if I forgot to say, and of course I forgot to say that yeah, the global minimum, but in general close to the goal, no? To remember x hat close to the goal in order to go to this value at least as a mean value. At least as a mean value. Okay, but about that I told you many times. I don't remember what I told you, but anyway, we can go in depth through the projects together. Let me go ahead. Jacobian. If I consider this system here with equation 1, 2, 3, we have this Jacobian. Let me justify just some value, 0, 0, 1. Here we have the derivative of this x3 of k with respect of x1, which is 0, because we don't have on the right part any dependence of x1. The derivative of this x3 of k with respect of x2 again is 0, and then the derivative of x3 of k with respect to x3 of k minus 1 is 1, 0, 0, 1. Look at this line here in the middle. Why TS? Because, excuse me, here I have this expression here, which is the x2 of k, which is x2 of k. The derivative of x2 of k with respect to x1 of k minus 1, the first element, is basically ts. We can see ts multiply x1 of k minus 1. This means ts. Why this expression? Because this expression here is the derivative of x2 of k with respect of x2 of k minus 1. If you remember the definition, this means 1 minus 4 times ts x2 of k minus 1. If you do the derivative with respect of x2 of k minus 1, it's exactly this. Yeah. This is a little bit too some elements to be verified, but believe me, but try to do at home. Also, these three elements can be very easy justified. Sometimes I'm using also, as I told you last time, the Jacobian, symbolic Jacobian of the MATLAB, or yeah, we can do it so by hands, but we can make mistakes. Why this zero here? Because it's the derivative of, excuse me, yeah, of x2 of k with respect of x3 of k minus 1, the third variable. We don't have here the influence of x3 of k minus 1. This means zero. Exactly. Everything, please pay attention, calculate it at the previous corrected state. In case which we have here something which depends of uk minus 1, of course I have to put here uk minus 1, but uk minus 1 is known because it's the output of the controller typically. But in any case, it's something which must be known because you remember the derivative, the observability depends on the input. This means the input must be given. Going ahead. Yeah, look at this possible, let me say, representation. Here the students make a little bit some mistakes, but it's not, let me say, it's not a big problem to do. I show you what I intend with this nomenclature, because a k hat is not there. But the reason is sometimes, as I told you in my manuscripts, I'm not so precise. No? Look what I am trying to explain. What I told you until now, basically this representation is a centralized representation. I don't know if in my manuscript is a little bit better, more or less the same. I mean, in Kalman filter, we have here x1 hat minus. Here we have x1 hat. What we have on the right part is with hat. What you have in the left part is hat minus. You remember the a priori estimation. Of course, here is not, in this form, is not inside the Kalman filter because, of course, before putting everything in the Kalman filter, we have to build the model. I skipped this part of the Kalman filter. In any case, a k hat does not exist in our case. I could read that in my is a little bit better. Let me see, because I see an error. Because the students make an error here. This is not hat, is x hat minus. Look, let me go to my manuscript, because as I told you, it's a shame the slides the slides are generated this semester. Of course, we can see that for the student it was not so easy to distinguish hat and minus. It was my calligraphy is not clear. No? ZK, ZK, or YK, I don't know, I don't remember the notation, but in any case, this H function is a function of X hat minus of K. The students interpreted this minus as a hat of K in this sense. Let's explain the meaning of what I am doing. We have a scene and a centralized. Let me go ahead with mine. We started with a centralized structure, or if you want, with a centralized Kalman filter, which we implemented in different forms, in different exercise before today. Look at this. I am trying to tell you that I can represent my system now with two state equations, for instance, equation 2 and equation 3, and an output equation considering the equation 1. But of course, we can consider also two different representations. We have three equations which can be combined. Two equations in states and output equation. Of course, we have three possible representations. Also, this open a question. The question is, which one is the best representation? I will try to answer or to address this question later. Let me consider this possible, let me say, representation, which we can see if you remember one of the first lecture in EKF, which the output representation is set of k or the y of k equals h of x hat minus of k, comma 0. Comma 0 means we didn't consider in the model the measurement noise, because the measurement noise is something which plays a role in the algorithm, in the calculations. But of course it's there, which characterizes the uncertainties on this equation. At this moment, we are considering an output equation x1. But of course, I can consider also two different representations, in which we have x1 and x2 and x3 as an output, and we have x1 and x3 as a state, and x2 as an output. But let me consider this. In this choice here, we have x2 and x3 as a state, states, because the output is characterized by the equation x1. In other representation, I can consider x1 and x2 as a state, if I consider x1 and x2 as a state, and x3 as an output. Possible choice. Or the last choice is x1 and x3 as a state equations, and x2 as an output. Of course, I have to define, once I define the state representation, I have the state variables. Here, again, the state representation x2 and x3, and then the states are x2 and x3. State Jacobian. Why this? Because I have to do the derivative of x2 of k with respect of x2 of k minus 1. Because the state is x2 and x3. Why this one? Because you have a 1 minus ts multiply 4 multiply x2. Again, I do the derivative of this expression with respect of x2 of k minus 1, because at this position here, we have x2 of k, the derivative of x2 of k with respect of x2 of k minus 1. And this element here, no? We already did before in the context. Why we have 0? Because it's this expression here, which is x2 of k, this means the derivative of x2 of k with respect of the other states, with respect of x3, but at time k minus 1, in accordance with the definition. 0, because we don't have. The same can be done here, no? Why this is 0? Because the derivative of this expression here with respect of x2 of k minus 1 is 0. We don't have x2 of k minus 1. Why is 1? because it's the derivative of this expression here with respect of x3 of k minus 1. This means 1. It seems to be that this diagonal matrix generates problem in the sense of the observability. Do you remember? I told you that diagonal structure in the matrix could generate a problem, but it's not in our case because, as I told you, that is just, remember, I insisted on it's just not a representation of the whole system. I didn't check here the observability, but believe me, if you check the observability of the, let me say, of this, let me say, original system, you will realize that the system is observable. This means it doesn't matter in which form I will represent the observability. Yeah, or at least in this case, we will not lose the observability. Of course, should be nice to test, but everything. But believe me, why nevertheless is not we don't lose? Of course, it's just in a different representation. The information basically the same. This is a little bit the reason. But of course, mathematically, here, the question of students convergence exactly means the observability. I don't want to insist on this topic here, but the problem is of KK change over time, or basically if this product is consistent, in any case it's not zero. I can insist on these calculations, but let me think just that nevertheless the system is connected, is interacting. The three elements which we have here, x2, x1, x2, x3, are connected through the output. Through the output. If you remember, this J here plays a role in P minus. In P minus. I don't know if you remember, because P minus is J multiply P K minus 1, the a posteriori error covariance matrix, multiply J transpose plus Q. Plus Q. It seems to be that the system is not connected. But the reason is why it's connected, because the system is here connected through this equation here, which basically, let me say, is reflected here with H. I show you immediately now. Because if I calculate this, H capitalized, the Jacobian and the output of this expression, we have the derivative of x1 of k, the output, H not capitalized, H not capitalized. Here we have it, zeta1, x1, in accordance with our notation. Before I told you z, but x1 equals H of x hat minus of k. Basically, this expression. This is x1 minus of k. Yeah, x1, because I am measuring, equals this expression. The Jacobian, which plays a role in kk, which is not zero, is calculated here. Basically, x1 of k with respect of x2 of k minus 1, why x2 minus of k minus 1? Because the state x2.
Professor,
yeah.
Mercurelli, it's hard to see because the light is reflecting from this file.
You cannot see well?
Yeah.
Better?
Now it's good. Thank you.
Yeah, stop me if something technically also the content is not clear. Now, this element here can be justified because the derivative of x1 of k, the output which is this expression here, because also here I didn't put in the notation of Kalman, but we have to think about everything is in Kalman in this sense. Here is the output equation, and basically this expression here is, yeah, this expression here. The derivative of this expression with respect of x2 of k minus 1, if you look here, is 2 times, no, excuse me, 1 times, let me see. Yeah, 1 times x3 of k minus 1, because it's just here, no? The derivative of this expression with respect of x2 of k minus 1. Ts multiply x3. What about this? Is x1 of k, again, our output equation, if you want, with respect to x3 of k minus 1. If you look here, this time this is 2 ts multiply x2. And we have here. Yeah, and then we can see is this product here is not zero. The question is how sensitive. This is another question. We can see that depends also from TS. TS very small, phase 2S, that the system is not so sensitive because the product tends to zero or tend to be small. Advantage, nevertheless, to realize the Kalman filter in output, it has basically, we have small system in the sense of observability, but in general, computational, we can see that here we have a 6 value, 1, 2, 3, 4, 5, 6 in the Jacobians. And here we have 9 values, no? 3 times 3. But in general, as I told you, do you remember, using state Jacobian smaller, let me say the level of the observability will increase. Of course, here we have the problem, nevertheless, to be evaluated by the presence of TS. If TS is very small, this approach here is object of our evaluation. Another variation of the variant in the output Jacobian is exactly what I told you now. Look, this is the output equation. If we are considering this, when we are considering this, if for instance, slow dynamic for x1, and TS is very small. This means if x1 of k equals x1 of k minus 1, I can cancel. And I can rewrite everything as in an output equation in this form. And the Jacobian, believe me, if I recalculate the Jacobian in this form here, we have a different Jacobian which does not depend of TS. Of course, does not depend of TS because we don't have any dynamics in the output in this sense. This is something which should be considered in this sense. This means, yeah, of course, could be done this approximation, but is valid or bring in our case something in this sense if this assumption is not conservative, slow dynamics, and eventually TS is very small. The advantage here that we don't depend on TS, as of course is an approximation, but nevertheless we have a more sensible system. This means more sensible means the Kalman gain change, even though TS is very small. Change something more. Change something more. This could be an advantage. But of course, we approximate the output equation in this sense. Now, let me implement this. Let me implement this And then we will discuss everything. We will see in the example which I have, we don't have a big difference between this variation here and the first variation. And then I will tell you something interesting in the estimation of TS as a possible element to be estimated. Let me switch on MATLAB. Let me switch on MATLAB. So I will discuss a little bit. I need a second to upload MATLAB, but I think should be not take much time. Let me wait a little bit. Yeah, it's opening. I think I opened. Oh, 1 second again. Okay, I have it now. Let me share. Okay. Okay, before those, let me. Okay, let me share now. Okay, let me open. I will upload everything in my study, believe me. I think it is one. Let me see. I have to wait again for. Don't forget here we measure x1. Huh? I mean, in the equation here, let me show again what I intend. We measure x1 because x1 is the output equation. This means we have this value here, this value here, this k, 1 second. This came from the estimation, this came from the estimation, this came from the output of the control. Let me show you more concretely with Simulink MATLAB. Look, here is exactly the system. We can see the parameter A, which must be defined, which must be given to the system, but Kalman filter does not know. I will put a 0, for instance, in the initial value, totally wrong value. Everything which is here around represent the system. I don't know if you remember, we had here the derivative of x1 me see a little bit better. The derivative of x1, which is equal what? U plus a multiply x2, I don't know if you remember, minus 2 times x1. If you look at Ohm, what I implemented, or what I told you before, we can also justify this expression here, but it is easy to do because we can see that is x2 derivative, which is equal what? Do you remember? x1 of k minus 1, or the x1, let me say it quickly, minus, do you remember this nonlinear factor, minus 2 x2 square. Just to now, if we go in the workspace. Oh, where is, yeah. And I put, I don't know, I don't remember which one. It doesn't matter which one. 3. A equal 3. And the TS equals something like that. About TS, I told you that nevertheless we have to be careful. No? But about TS, I will tell you a little bit later. The idea is now to justify together or to look together how the Kalman filter is organized. To repeat a little bit, here we can put also the noise in the measure of x1. Remember, we measure x1. If you don't have noise, better. No? No? We need x1 of k minus 1 because we measure x1, but in our Kalman filter structure, let me show you, we have x1 of k minus 1 to generate the output. I show you now inside the Kalman filter in MATLAB. If you go here inside, here, again, we delayed of TS because this is the input U. The input U. Here is just a constant, but of course, in the real case, is the output of the controller. Look, in the output we have in the argument of this function we have xy measured, delayed, u measured, delayed. TS again, yeah, I can put TS here as also as an argument, but in any case should be the same as I put in the workspace. No? Here we have x2 and x3 in our representation as the state variable. You remember this if empty, all the states represent the initial value. Is active, this if here is active just at the beginning. The same here, no? The old covariance, the a posteriori covariance. Do you remember in the interpreted file, we gave the initial value externally, let me say. Here we do everything internally because the key point, do you remember this persistent? I told you three times about this persistent. The variable which I have to be considered inside for the recursivity of the data, of the algorithm, if you want. Look, I changed the name in order to use the same notation as in the lecture or in the manuscript. We have here the variance of the measurement of x1. I don't know why 11, probably some student asked me to change something. Basically, we try with a round value. Yeah, this typically can be estimated with neural networks, with PSO we do here often with PSO, also here. Nevertheless, I put some values, but of course, this is not important question or the open issue in the Kalman filter because must be somehow estimated. Here in my lab, we use very often PSO. Very important to notice that the second equation in uncertainties, 1,000 larger than the first one. The reason is that the second equation is characterized by this, in this context here, but by the Gaussian variable. No, I show you which one. X2 x3 of k equal x3 of k minus 1. Exactly. Yeah, we have a comment. I see here. I see here. This is the, excuse me. Here again is the output equation. X1 measured. Ts, which multiply minus 2 x1 measured, because here was x1 are k minus 1, plus x3, exactly the output equation. Here you can see the output equation using the approximation. You can do at home if you want. You can consider, you can throw away this comment, and you can work with the second approach. Remember, x1 of k circa x1 of k minus 1. You will realize there's at least optically we cannot see any difference. Of course, if you measure, if you look at the variance we can do together, it could be that it's a little bit different. But I don't think so really much different. We can do together if you want. Here is the prediction or a priori estimation states. This 0 here states, I don't know if you remember, that x3 of k is equal to x3 of k minus 1. Because it's not updated. I mean, this is the updated element of the vector. This is the vector. Look at this. To be precise, is in a part of the field. The field is this one, which consists of this old vector, each time in a different vector, of course, because came from the a priori estimation. And this is the rest of the field. Of course, came also from the a priori estimation. We can see x2. But of course, I have to put the x1 measured because I measured x1. It's not a state. I don't estimate x1. The rest, no changes. I copied the Jacobian, the state Jacobian. I copied the output Jacobian. Of course, if you want to use the second approach, I have to throw away this comment. No? We can see, I don't know if you remember this expression here, assuming that x1 of k is equal to scan of k minus 1. I try to show you. Yeah. x3 divided 2, x2 divided 2. Hat, here is hat. Here is not calculated inside the Kalman, but is hat inside the Kalman. The estimated at the previous state, at the previous step, excuse me. The assumption is this. I will try to show you the difference between, 1 second. The rest does not change. Again, the Kalman filter, the structure of the extended Kalman filter is always the same. It depends then which dimension and so on. I don't have to. Yeah, basically, I copied. Do you remember we discussed together the state Jacobian, and I copy here the output Jacobian. Okay, let me run. Of course, here the test is just to look at the estimation of A. If A is well estimated, A was equal 3. Well, okay. Let me say at least steady state estimate. I didn't invest time to tune. You can imagine that I will estimate in any case x1 and also x2. X3 this one, yeah, the second variable. Let me see. Yeah, we can see that at the beginning we have a big error, it's absolutely not well tuned, but I hope that we get 3 here, no? Somehow. Yeah, it seems. Let me see if I am able to, I don't know if I shared. Believe me, optically, I cannot see any difference if I apply the second variation. Let me see if I am able to look here what happens. Yeah. I think, comma, I don't remember really. Let me see the 1 second, the syntax. If I define the different output, let me see the syntax, but I think comma. I'm looking for in the help. Yeah, I remember well. Okay, are you here? Let me see. Uh, how, why doesn't it show? Outcove. Huh? Exactly. And at the end, yeah. Uh, let me see. Let me. This here, no? Do you remember these 2 lines here are extremely important, 64 and 65. Why that? Because states the recursivity, what we have in the correct covariance, what we have in correct states are used for the next step, thanks to the permanent, persistent, excuse me, persistent, which states in the permanent existence of variable, let me say so. Okay. I have another output. Let me see here. Now I don't remember. I think you should understand MATLAB. Let me show you. It could be that it's very small, the difference in the covariance, basically the error, no? In the estimation. Okay, let me show you. Okay, let me show you if I'm able to view the legend. Okay, we can see here, no? Here the estimation of x2. It seems to be 8. Let me write this value. I have to call, I have to stop a little bit the lecture. But let me, so basically the estimation, I need something to write now. The estimation of the variable x2, they have a variance, I don't know. Let me say 7,9, no, I don't, it's so small, 978, no? the estimation of x2, the first variable. Huh? Let me come back. One second. And then we have here the estimation of x3, the last one. Here is did you able to read here? Oh, it's so small that I'm not able to see it. Ah, could be that you have the possibility to read somehow. Uh, I don't know. No. 5,600, something like that. No? X3 is the variance, no? Because the diagonal. No? Do you remember? The first one is the first element of the diagonal. The last one is the second element of the diagonal, no? The variance. I read here 5,000 by 5,696, something like that. I don't know. Okay. Let me now go to here again. Let me go here inside. And let me change with this hypothesis. No? This is the new output Jacobian. And this is the output. Not the 32 anymore. If you want, I can comment, but it's not necessary because the system will take the last one. Let me show you if it's visible also numerically a little bit the difference. Then I have to stop in 1 minute and then I will come back we conclude with okay, let me share this. Of course, we have the possibility to read directly in Simulink the value. It seems to be that this is much better, could be, but what I am asking, why the other was so big? Let me see the other one. It seems to be better, this approximation, with the approximation. Let me see the first one. First one is the yeah, the other one was 7,9. Here's basically the same. But I am asking why the other approximation was so bad, or I was not able to read the value. Please try to do at home. Try to do at home again. It seems to be that the second yeah, the approximated is it seems to be better than, or probably I read the wrong, is 5.6. We have to check again at home. What I would like to show you now, very quickly, is this problem here. Look what I would like, the last consideration. Is a very nice consideration. Let me see if I have it here. Oh, I don't have, but I can rebuild. I can rebuild. Look at this example. Again, is an electrical example, but anyway, we have a differential equation. Let me do the discretization of this. Again, forward Euler. We have seen this example in different contexts many times because it's easy to be implemented -1. But conceptually, it's extremely interesting. Assuming that I would like to estimate the best TS. You remember about S, I told you many times, should be not too small, should be not too large for different reasons, should be not too small because I can reduce the observability. You remember I told you many times during the semester, should be not too large because otherwise the approximation is very bad. Mathematically, you remember the Shannon theorem, if you remember engineer, but if you don't remember, it does not matter. It's intuitive to understand that Ts very large, Ts very small. We have something, we destroy the dynamics, or we don't represent very well the dynamics. It seems to be the current constant. But if I have an input, physically is an input, of course, the current is not constant. Ts very small, we update it very roughly. It's very large, excuse me, very large. Because we don't know what happens in between. Or if you want, if you remember Shannon theorem, Ts must be considered, or the simple time should be at least twice of the maximal frequency which we want to represent. But anyway, this is more technical for engineers. What we think is, why not to consider this Ts as an augmented state? And this means I can consider here, in this context here, Ts of k-1. If this is an augmented state, it's not a constant, change over time, over k, in the sense that our time in discrete is k. And I can show you, but I don't have time, but it's intuitively easy to understand. If I formulate, or if I try to solve this problem of calculate S additively, directly here, Kalman filter does not find a solution. We end up with non-convex problem. The reason is that this problem here, or this formulation, this augmentation, came from this problem of this representation, physical representation, which Kalman does not accept. Excuse me. If T is dt, think about the I equals everything multiplied by dt. I mean, this kind of approach came from this kind of approach, physically, because the system physically is this one. U input of T. But if I augment in continuous, we have something like that. But this means 1 equals 0, which deterministically it's something difficult to be justified. Until now, we have seen, do you remember, R of k minus 1 equals R of k equals R of k minus 1. This means constant. No? R of k, constant. But here, it's difficult to give this a meaning. And Kalman filter realized this. Kalman filter will not converge. What we can do, nevertheless, with this possible representation output, please reconsider our original problem. If I try to augment in this sense, Ts here inside will not work. For the same reason, the physical reason which I tried to explain. But look at this expression here. I will consider a different augmentation of the state, Ts tilde equal Ts tilde of k minus 1, a constant tilde at each step, but in the context of the states. But it's not this Ts here. Isn't it different? These Ts tilde appear in the measurements. This means I will try to estimate Ts tilde in this possible representation. And then once we have a Ts tilde, I will update to Ts. This means I don't say to the Kalman filter that Ts is our state. I will say that Ts tilde is our state, which nevertheless Ts tilde realize the update of the measurements. This means in the context of the Kalman filter, Ts plays a role in the optimization. Because in a pseudo state, which he has. This is just a sketch. I show you the simulation. And then if you want, you can work at home a little bit. You can consider a project together on this. No? The Jacobian is not much different as before. I mean, this minor here, the left up corner 2 times 2 minor is exactly the same. And y001 is easy because if you look at this equation here, it's clear that here we have a 0 because here we don't have Ts tilde. The same reason here. No? Just here because this derivative of Ts tilde of k with respect of Ts tilde of k minus 1, which is 1. This derivative of this with respect to Ts tilde of k minus 1 is 1. 0 here, because here we don't have the dependence of x2 and x3, k minus 1, of course, in both cases. Here we have the Ts of k with respect of x2 of k minus 1, which is 0, because we don't have. The same here, no? This derivative of Ts tilde, of course, I forgot to say, of k minus 1 with respect of x3 of k minus 1, which is 0, because we don't have here. Please remember here is the state is Ts tilde, which is not basically the Ts, let me say, which updated state. It's Ts which update the measurements. And then I set, once I have a Ts tilde, I set Ts equal Ts tilde. Let me show you quickly the simulations. Look, here's the new files. No changes here in this sense. The unique aspect is here. Here inside both, I put Ts tilde because once I calculated TS tilde, I will update to TS. Of course, at the beginning, Kalman filter does not know, oh, I can put TS tilde equal TS. The same here. Eh? The same here. We can see that it's red because let me say the Kalman filter does not yet. But look, I will initialize with TS. Let me show you. I will put TS tilde, this is this, no? Equal TS. TS is defined to start. And then let me analyze the Kalman filter inside very quickly. But it's basically the same. I just augment it. You can see here, I will start with TS and TS tilde. Now the new states is TS tilde. Everything is 3 times 3 in terms of covariance. We can see here TS tilde as the state number 3. 1, 11 on 10, I don't know why it is 11, just really irrelevant. We can see that we have now in a matrix QX 3 times 3. I put this very small covariance or the variance variable for TS tilde. We can test how robust is eventually in a project. We can go in depth, of course, in a project. This is really advanced. I am considering the first variation. Of course, it seems to be that the second one is better. This should be also considered in the possible projects and in this example. And the rest I copied from my calculations. Of course, I am considering the first approach. The rest doesn't change anything. Of course, the dimension here, before we have 2, because the state was 2-dimensional, now we have a 3 in the states. Look what happens. I hope that is working. At the beginning, I start with TS equal TS tilde, and then I pass the value. TS tilde is here. No? Seems to be that doesn't work. Let me see. Oh, probably I didn't. I have to run, huh? Or yeah. Now it's running, excuse me. Very interesting to look at TS tilde this year, the truth variable. Huh? Let me see. Yeah, of course, this could be, anyways, an analysis of a project. Now we can see that I am starting from 10 up to -3. I did include, excuse me. Ah. Ah. Yeah, believe me, we have, I mean, 10 up to minus should be, I'm not able to see, but should be somehow. Anyway, I'm not able to look, but anyway, we can see that at the end we converge to a different value. And it's not so much different because the variation is very small, but in any case, it seems to be possible, this approach. Possible, this approach. It could be an interesting project to analyze together. Let me see just one thing that I need to call, as I told you, that we will come back to speak if you want about the projects. Otherwise, we can organize meetings and so on. Let me come back to the simulations. Yeah, this I have to close. Let me simulate again with the different values of variance. Let me see t tilde here. Simulating with different values. Yeah, we can see that here is the initial value. It is very small value, no? I'm not sure if we can trust this value here. I mean, it seems to depend on the variance, but also I am sure that it depends also on the signal here, no? On the signal here. This means should be nice if we can consider this in a possible project to be analyzed. Of course, is an approach which can allow us to say it could be that we can also estimate an TS. Because if I directly include TS as a state, we have seen that in a physical, um, let me say, yeah, contradiction, 1 = 0. But of course, we have seen just on this example that depends of the variance which I put. But also, believe me, I don't know if I have now quickly the possibility to show you that it depends also on the signal. This means could be interesting to analyze this in the context of the project more, let me say, in depth. Yeah, you can see, yeah, how different is now. Let me simulate longer. Anyway, this could be nevertheless something to be analyzed. Let me stop now. I have to call. I come back here for you if you want to discuss some projects. Otherwise, we can rearrange a meeting anytime. I would like to say per Zoom. Let me see the results. Yeah, it seems to be decreasing, but it could be we can tune a little bit better in order to, let me see if I'm able to do quickly. I come back in 1 minute. No? Okay, let me see what happens now in the simulation that we will conclude. But of course, this is you can see it. Of course, we don't have a big variation, but we can see that it could be an idea to analyze this kind of approach in order to estimate in a suitable TS, but considering not TS as a state, but something which is similar because it's the increment in time, but in the measurements. Because if you try with the TS at the state, we have um, this contradiction, which I told you at the beginning. Yeah, of course, here we need uh, to do some, of course, the difference that we can see is not much, but it could be that we can show that probably we have a better result in which term? In term of mm, covariance matrix, to be precise, the sum of the yeah, element, you can see probably I have it here. No? Very quickly, we have to dedicate more time. Here we have the covariance. Here we have 9 elements. Let me show you. Why that? Because you have a matrix 3 times 3 in the uh, in the state representation, and the element of A was the fifth 1, 2, 3, 4, and 5. I think this one. Oh, why does this is the variance, I think, of the A. It seems to be increasing. I'm not able to read here the value. 10 up to 5. This is a little bit strange. Let me see the approximation of A. Oh, excuse me. Is this one? Excuse me. Here, this should converge to 3. Yeah, probably. Yeah, it could be that will converge. I am not sure. We have to check this. Of course, the tuning, as I told you, is not far away, but I hope that it is not diverge. But of course, we have to tune a little bit better. But this moment, it does not means that will not work. No? Somehow, if you remember optically, it seems to be better than what we have seen with not adaptive TS, because you remember we had at the beginning a big error is negative. Now, yeah, again, this is just a way to, how possible to say, to show you that is a possible project. It seems to be oscillating now with the new parameterization. but we have also. But anyway, as I told you, this could be, I presented, it could be in a possible topic for a project. Okay, let me stop now the lecture. Thank you to be here. Of course, thank you for attended these classes, this lecture. And let me conclude. And I am here if you want to discuss the project and so on. I will upload everything in these days, believe me. Thank you.